Bismillahirrahmanirrahim. Assalamu alaikum. We have got an interesting example of a harmonic oscillator which assumes this ordinary differential equation, which is second differential equation, x double prime plus 4x to be 0. This is an undamped harmonic oscillator with mass 1 and the spring constant as 4. We can convert this into a planar dynamical system. What we need to define is we just define x prime to be equal to, let's say, y. Okay, so when x prime is equal to y, then x double prime will be equal to y prime. Okay, and this x double prime will be equal to y prime, so I can write here y prime. Okay, plus 4x equal to 0. Or I can write x prime equal to y and y prime equal to minus 4x. Now I can write it into system, which is x prime, y prime and 0 1 minus 4 0 x y. Now you can see that this is not the canonical form. So what we can do is we can play with this matrix A, let me call this, and we want to see first what are its eigenvalues. If they are real and distinct, again we will find out its eigenvalues, and then we will calculate t, then t inverse, and then t inverse at t. If they are complex, again we will be following the procedure. So let's first find the eigenvalues of this A. Matrix A is 0 1 minus 4 0. So determinant of A minus lambda I will be equal to minus lambda 1 minus 4 minus lambda, like this is kind of the determinant sign. So like it's going to be lambda square plus 4 equal to 0. So like lambda is plus minus 2 iota. Okay, so I have two eigenvalues. Lambda 1 is 2 iota and lambda 2 is say minus 2 iota. So these are complex, and previously when we were developing the theory, we have already realized that we will only consider one eigenvalue and we will find corresponding eigenvector. So for lambda 1 equal to 2i, we will find out eigenvalue. So for eigenvalue, we need to solve a minus lambda 1 I operating onto x to be 0 column vector. A was 0, and then we had 1 minus 4 0 minus this is 2i, identity is 1 0 0 1, and all of this is operating on xy set to be 0 0. Then we have minus 2i 1 minus 4 minus 2i operating onto xy set to be 0 0, and this gives me minus 2ix plus y equal to 0 and minus 4x minus 2i y equal to 0. So this is just single equation. Basically, if you multiply this equation 1, this upper one, with minus 2 iota, then you can get this one. Okay, so we can consider only one of these, which is, because both are same, 2ix. If I set x to be t, then y is 2ti. Okay, therefore vector should be v equal to t comma 2ti. In other words, which is 1 comma 2i. And now this 1 comma 2i can easily be written as 1 comma 0 1 0 plus I 0 2 0 2. So this is my v1 and this is v2 as we have discussed in the theory. So I have v1 and v2. Now I can find out this t, which is v1 means 1 0 and v2 means 0 2. You can conclude that t inverse is 1 0 0 1 over 2. Now we will find t inverse a t. T inverse is 1 0 0 1 by 2. A was 0 1 minus 4 0. T is 1 0 0 2. So 1 0 0 1 by 2, and then we have 0, and then we have 2, then we have minus 4, and then we have 0. If we carry on further operations, then this is going to be 0, and this is going to be 2, this is going to be minus 2, and this is going to be 0. Do you recall this form? We had considered this case of x prime equal to ax, where a was 0 beta minus beta 0, means when a had purely imaginary eigen values. So our system has been transformed into this y prime equal to 0 to minus 2 0 y, and this has purely imaginary eigen values, and this is in canonical form, and you can see that beta is equal to 2, which is greater than 0. So this system is showing a center with clockwise orientation. Okay, clockwise orientation. So what we did, we had a system x prime to be equal to 0 1 minus 4 0 x, and we converted it into another system which is 0 2 minus 2 0 y. These are two different systems, but in fact they are related through some transformation. What we have done, this was not in the canonical form, this is in the canonical form, and we have converted it, this x prime to be this one, with the help of certain transformation, which is t inverse a t. What has happened in the phase portrait, I can show you on that. But before that, if we talk about the solution to this, let me tell you how the solution to this will look like. So we have done this in the previous cases of purely imaginary eigenvalue case. Okay, so the solution should look like y of t to be equal to c1 times cos beta t minus sin beta t, okay, plus c2 times sin beta t and cos beta t. In fact, this y of t is solution to this system. If you just multiply our transformation t to this c1t multiplying to this c2t multiplying to this, then this will be the solution x of t, which will be the solution to this. Okay, so now I'll show you what is going on the phase portrait. So this part is for y prime equal to t inverse a t y. Okay, so when we had a system x prime equal to ax, we converted it into this form, and then this is the phase portrait for this. But the original phase portrait to this original system was this one, and from this one how can I get to this is just because y of t is solutions in this. So I'll just operate t on y of t and I'll be moving to this. Okay, so these both are same, like nature wise, both are center and both have the direction clockwise. Okay, so the advantage of this canonical transformation is that once the system has been converted into the canonical form, then its phase portrait becomes easier to make, like this one which we have already considered. But once we have the solutions like these, we just operate t to these solutions and we will get the solutions originally we have, which ones. Okay, thank you.